Okay, hello everyone. Okay, let's start today's lecture. So today we are going to talk about the applications in bionic limbs. Okay, so this slide shows the learning objectives. So today we will briefly talk about the motivation. Okay, why bionic limbs? Okay, and then we will briefly see together the from passive prosthetics to myoelectric prosthetics. And then we will finalize with topic of toward the neuroprosthetics. I will briefly introduce the recent trend of the bionic limbs. Okay, first of all, let's briefly talk about the why bionic limbs. Okay, so I have to talk about the amputation. So as you can see in here, okay, so amputation. Okay, so actually, regarding to uh the United States. Okay, so United States statistics. So roughly 2.1 million people, okay, living without limb. 2.1 million people. And then 185K people have an amputation each year. And then more than 500 people lose a limb each day. So actually, so many amputees are there. And then even in South Korea, so I got this number from the Seoul Asan Medical Center. So 46 patients in every 100,000 people undergo amputation surgery each year. So also Korea, there are a lot of the amputation. And types of amputation, usually we refer to upper limbs and lower limbs. So when we look at the portion, the lower limbs percentage are a little bit higher than upper limbs. Okay, so what is amputation in Korea? 절단, right? So in here, the surgical removal of all or part of the limb or extremity such as an arm, leg, foot, hand, toe, or finger. So all of these kinds of the removal, we indicate amputation. So in here, briefly talk about uh, the what causes the need for amputation. So historically, amputation have happened due to three main reasons, like trauma, okay, disease, and war. And yes, disease such as here, the blood vessel disease and diabetes is really one of the main reason, okay? And also accident and trauma, like car crashes, industrial accident, even natural disaster. And here for the arms, 75% of upper extremity amputation are related to the trauma. Okay. And nowadays war, okay, and conflicts, explosive gunshot injury, landmine. But here the point is amputation is not only a medical event, but also a life-changing social and personal issue. Okay. So in the past, in recently actually, the surgery doctor has kind of the dilemma, okay, to save or to amputate. Okay. So also this issue, I heard a doctor from Seoul Medical Centers, okay, in the past, they prefer to save the limb even at all costs. But thing is, it sometimes result in just repeated surgery, okay, and continuous infection, a lot of pain. So that's why once some a patient if lose the timing to block all the disease, and this amputation become higher. Okay, so that's why the proper timing is really important. But in point of view of the doctor, they what a lot of their role is to save the limb, right? So that's why in the past they try to save the limb. But these kinds of the issue, like poor long-term outcome. Nowadays, due to the development of the technology, also they prepare to amputate in early, okay, and planned, so which actually can give better future function nowadays. Okay, of course they have to really carefully design the amputation plan and also have to persuade the patients. So this it's not only medical, okay, I mean the amputation, and it's about the patient, the future life. So that is really important. So also I joined kind of the open surgery for the amputation before. That takes a lot of time and quite make yeah, how can I say, desperate, really desperate. Once someone lose the leg, okay, so that's why actually this is not easy to determine, to amputate, right? Okay, so nowadays, anyway, the modern perspective, it is better to do amputation, right? It really needed. Okay. Okay, then let's briefly talk about the amputation. Okay, so even here, this figure roughly shows the major categories of the upper limbs amputation. Okay, so of course there are also lower limbs. So that one I will present later if we have time. Okay, so for example, at the end of our hands, around the wrist, okay, this is we call wrist disarticulation. Okay, limb is amputated at the level of the wrist. Also, there's hand and partial hand amputation, like finger, thumb, or portion the hand below the wrist. And then there is a transradial, okay, which indicate the below elbow amputations. So any amputation occurring in the forearm from elbow to the wrist. And above the elbow, we call transhumeral amputation. So any amputation occurring in the upper arm from the elbow to the shoulder. Shoulder disarticulation, okay, at the level of shoulder, which a shoulder blade remaining, the collarbone may or may not be removed. And four-quarter, okay, amputation, which is one of the really, really challenging in terms of the surgery and in terms of the after amputation. I mean, when they would like to use the prosthetic, like robotic arm or bionic arm, because the remaining part is really short, so that really difficult to fix or hang, okay, to modulate, to control the bionic hands. Actually, here's bionic arm, right? And then also get the information from muscle and nerves is also quite limited. Okay, so if you are an engineer, right, and you have to design the bionic arm, bionic hands with neurological signal, right? So depending on the amputation, right, then you have to plan differently. So for example, like here, this is one of the example, like here, transradial amputation, right? There's a below elbow. Even this transradial amputation, depending on the length of the residue, okay? So also plan slightly different, okay? For example, this figure shows the transradial amputation, okay? And here, natural rotation means if the amputee has very long, okay, the residual limbs, right? Then they still rotate it more than 180 degree. Okay, so we called this is the pronation, okay, and supination. Okay, this is talking about this one. But if the length is reduced, then actual rotation, okay, angle also reduces slightly. Okay, then you have to consider different circuit and different function for your hands, right? So this slide briefly shows the long remaining still 100 to 120 degree of the pronation and supination can still utilize the long length of the residual limb so that it shows the excellent capability for prosthetic restoration and lifting. But medium, here indicated around here, still able to fit moderate weight. Okay, still have some length and utilize elbow without problem. But for the short range around here, it presents problem with the suspension and range of the motion. Residual limb significantly low pronation and supination as they become shorter. It means bionic hands for short, okay, length of the transradial amputation, okay, should have pronation and supination function. And another example is a transhumeral amputation. So transhumeral amputation is here above the elbow. Also in here, depending on the length, long, medium, short. Also here it shows some kinds of the issue. Okay, so provide muscle power, a range of the motion necessary to produce very functional result with conventional prosthetics. Medium size may still permit, okay, the functioning of the prosthetics, but serious constraint on the placement of control cable used to operate prosthetic elbow. Short actually is insufficient leverage to control the socket position. Long residual limb is prepared for optimal prosthetic restoration. Prosthetic components can be externally powered, body power, passive, or combination of these. Okay, so that's why also this issue is can be connected with previous issue, whether doctor, if determined quickly and properly, then still the patient can save their length of the residual part. Okay, if they miss it, then amputation site continuously going up. So that directly affect these kinds of the following solution: prosthetic arms, prosthetic hands. Okay, then let's briefly talk about the from passive prosthetics to myoelectric prosthetics. Passive prosthetic, you can imagine in that like really old version, the literally passive types prosthetics. Okay, so prosthetic hand, like a static, just considering the shape. Okay, no function. Adjustable, slightly move, but very, very short. Okay. Prosthetic tool, like static. Actually, this is for customized design for specific function, like here, cycling, right? Could be the playing tennis, playing guitar, something like that. Adjustable with slight function, probably just 1 degree of freedom, very simple, straightforward function. Still all the things, the passive things, okay? And then when you look at this one, from passive prosthetics, so next version is we call the body power prosthetics, okay? So these kinds of the harness and cable, okay, so that they can control, okay, these kinds of the hands, very simple. Okay, let's see this one together.
It's attached to a cable. It's like a bike brake cable. When I move forward, it bends the elbow, or if I spread my shoulders out, same thing. If I stop and lock the elbow, the same motions will open the hook, which closes on the force of some rubber bands. It's confining and clunky, really not much more than a hook on a stick. It's better than nothing sometimes, but not always.
Yeah, he mentioned it's better than nothing sometimes, right? So very straightforward, but literally body power, to control very simple, okay, motion or function. And nowadays, like due to the 3D printing technology, they manually fabricate kinds of adjustable terminal devices. You can see this one as well.
Pues yo, tipo, con el reloj me sostengo, puedes sostener mi mano. Y pues este es un scratch donde yo pongo mi mano con el reloj, lo ajusto. Y como lo ajusto con el reloj, luego cortar la muñeca, esto me iba a cerrar. Y se me alcanzó. ¿Qué vamos a hacer? Loco, se puedo usar de los dedos y
Still, it depends on the body's about the movement, body movement. So that still we can say is the body pulse prosthetics. Okay.
Pues yo la saqué de.
Okay. Still, this one, we cannot say the bionic limbs, bionic arms can be controlled by our intention, like our biological signal. Okay, so from body-powered prosthetics, now we can move to electric-powered the prosthetics. So one of the best example, actually famous example, is we call myoelectric prosthetics. Okay, so this is one of the example. You can see it still looks like a very old version of the myoelectric prosthetics. Okay, so we can briefly see still all the components the same. So socket. Okay, so we need to fix bionic limbs, hands or leg, to our body, so that we need the socket mechanically fix it, and then EMG electrodes. So myoelectric prosthetics means it can be controlled by muscle signal, so that these myoelectric prosthetics need EMG electrodes actually inside the socket, and then to get the signal, we need the amplifier. So EMG electrode receive the muscle signal and amplify by amplifier and transfer to controller. Okay, and then finally operate it. Here we call terminal device like wrist. And then this one is actually operated by the electric power, so that it requires the battery. Okay, so this is a socket. So also there's a silicone socket, okay, and plastic socket. So different socket design we can expect. And then as we already talked we discussed in previous slide, so all the patients has own different uniqueness of the aspect of the amputation. So everyone has different aspect of the shape of the residual limb, so that they have to customize, they have to get the customized socket. Also, that procedure is very tedious, okay? But anyway, once they got this kind of optimized, well customized circuit, and then connect to bionic limbs. And for the hand, myoelectric prosthetics, okay, motion control for hook hand, or a little bit well developed the hands, and also wrist. Okay, but usually they the wrist they manually rotate it. Okay, but this one also I will show you later. Okay, so attach terminal device to the prosthetics, so which provide rotation, pronation, and supination. Okay, so here, it's here. Rotation function is normally passive. Okay, they just manually rotate their own wrist. So permit interchangeable, okay? So permit interchange of terminal device. And then elbow, also external elbow hinge or internal elbow hinge, okay? Is also nowadays a lot of function actually developed it. So electrodes, as I briefly mentioned, so to record the muscle signal, we put the electrode inside the socket like this one. This is old version and fixed in a slot in here. But issue is, so we have to record the muscle signal quite clearly and reliably. But thing is, as you can imagine in that, because the electrodes is located inside the socket, which is hard material. So during the movement, if the interface between the muscle electrodes and skin has detached, right? Then lot of noise actually involved in there. So we cannot record the muscle signal clearly, which sometimes seriously result in malfunction of the bionic leg or limb. So that's why these kinds of the electrodes is really important components, especially for the myoelectric prosthetics. Or sometimes electrodes to migrate, electromigration indicated here. And sometimes due to the sweat, right, become the wet when they wear this for quite a long time with some daily activity, right? Then become sweat. And these kinds of sweat affect a lot to record the muscle signal as well. So that's why nowadays, these kinds of flexible electrodes, which actually fit well on the skin, as well as also silicone liner together. So because of this issue, in also our labs, our group also developed some kinds of, we call imperceptible the surface EMG. Okay, we apply it to actually lower extremity prosthetic control, neuroprosthetic control. So as actually the issue that I just talked in previous slide, you'd like to achieve the stretchable and breathable and reusable, repeatable, adhesive, and durable surface EMG electrodes. Actually, this is the final version of the surface electrode using microfabrication process. And then we attach the skin to record the muscle signal. So we evaluate it to the function of the EMG signal. And then finally, we attach our electrodes under the silicone liner and socket in lower extremity, okay, the patient, and then simultaneously record the EMG signal. Okay. Yeah. And another issue is the battery. So when we actually collaborate with the Seoul Asan Medical Center for lower extremity, okay, patient. So as I talked in previous slide, so one of the biggest complaint from patients in nowadays is actually heavy weight. Okay, so they feel bionic leg still feel heavy, so that very young guys that does not actually do not care about that one, but elderly always complain about this one. Could you guys make a little bit lighter bionic leg, something like that? But when we talk with the company, actually that made this kind of bionic limbs, right? Actually, the weight of battery is significant. Okay, so that's why also one of the issue in nowadays is how to reduce the weight. Okay, so probably new battery developed it, then become better, right? Or we have to make very efficient, okay, motor operation. Then also could be the one solution, okay, becoming light. Okay, then let's briefly talk about the control. So myoelectric control. So myoelectric control is most common in electric system. Okay, so let's say usually if we use the SEMG, means surface EMG signal, developed it by muscle contraction. Okay, so that we record the signal. Using that signal, we control. Okay, so like this one, for example, this is the one of the EMG signal. So probably we can see from here. So in the last lecture, we talk about brief anatomy of the human body, like human nervous system, right? And then we talk about the neuron. So once action potential generated, right, and passing through at the end of the effector, then goes to neuromuscular junction, and then some nerve actually connected to the muscle fiber. So once this action potential goes to the neuromuscular junction, okay, then it actually release the neurotransmitter, which also finally lead to the contraction of the muscle fibers. Okay, so this one, a detailed process, probably we will cover later if we have time. Okay, also there are some kinds of process. So once muscle fiber contract, then also it generate kinds of the electric signal. So by putting the electrodes on the surface, okay, we can record this muscle signal. So usually we put two electrodes. One is a sensing electrode, the other as a reference electrode, so that we can differentially record the muscle signal, actually electrical activity. So like MUAP is a motor unit action potential, okay, is the electric response of each impulses. So once we record this one, okay, so for example, this one is a simple procedure. So electromyogram EMG signals are recorded from the surface of the residual using two electrodes. Okay. Neural signal goes to and then and contracting the muscle. Okay. Then two electrodes are placed on the limb, and one over the extensor and the other is for the flexor. Okay, so the location of the electrodes also we can put like this way, and also parallel put two near the one muscle. That is kind of the recording technique. Also, I will cover this in next weeks. Okay, during the recording neural recording class. Okay, then we record the muscle signal. Okay, so once we record the muscle signal, we can set the threshold. Okay, if that muscle action potential exceed the threshold, then sending the signal to close or to open. Okay, this is we call just a threshold-based operation. This is really, really simple operation method. So this one is the video we recorded in our lab. So one of my students just put muscle EMG, surface EMG electrodes. So whenever he tried to contract on muscle, the muscle signal will be recorded using the amplifier, and then we set the threshold. Okay, once we record the EMG signal from him, right? Then we know roughly which threshold level is suitable to operate it. Then once EMG, okay, oversee that one, then generate the signal. Okay, as you can see in here, only just one function. Okay, close, open. Okay, close, open. Okay, very simple operation. We can use it. And also in our lab, as I just briefly showed the surface EMG we fabricate before, right? I introduced in previous slide, the impulsive EMG. Also, we we applied to the lower extremity, okay, the patient, and then we asked them to contract a specific muscle. And then once this muscle exceeded the specific threshold, then we can send the signal to operate the bionic leg. Okay, also we did this on like this threshold-based very simple operation. And then actually in this study, we put our surface EMG electrode inside the socket and silicon liner, and then simultaneously record the muscle signal stably, and then wirelessly transfer to the another computer, so that we record different muscle pattern depending on terrain type, like just uphill, downhill, okay, go up, go down, and walking, just normal walking. And then I didn't put more additional data in here, but finally we used this EMG signal to one of the option of operation of the bionic leg. Okay, we did it. Okay, and then another example is, so because of the previous threshold-based operation, as I briefly mentioned, it's very simple task, only we can do it. Okay, so that is not ideal case, just a simple operation. Okay, so why don't we increase the number of electrodes, surface electrodes on the limbs, okay, to record a lot of muscle signal, okay? So then we can record like various of muscle activity patterns. Okay, using that one, using some kinds of simple algorithm, then we can define, okay, this muscle activity pattern, okay, directly connect to the specific motion of the bionic limbs. Okay, this is we call pattern recognition. Okay, so more electrodes, and we can get more information, and then we can have more chance to control the bionic limb, okay, freely. So for example, in here, if we put the 8 EMG electrodes, okay, then probably depending on the muscle activity patterns, right, we can then achieve this kind of function. And this one is also we got the video from Assam Medical Center, okay, that we collaborate together. So he just put the simple 2 electrodes and using simple pattern recognition with the AI, but not too difficult things, very simple things. Okay, so that depending on different muscle movement, okay, he recorded, and then depending on the muscle pattern, he just operated bionic hand slightly different. Okay. Also just try to grab it and drink. Okay, so now in commercial bionic limbs, still they try to use this pattern recognition method plus combining with the AI. So let's see one of the kinds of the promotion video from company. Okay, so here's Autobook, one of the famous
pattern
company in the world.
recognition controls terminal devices with artificial intelligence. The MyoPlus prosthesis control uses up to 8 electrodes to measure incoming signals of the forearm and derives patterns that are characteristic for individual movements. Complex mathematical algorithms transform and amplify these signals and patterns so that a prosthetic hand can translate them into the corresponding movement. The MyoPlus app is the central interface between the user and the control unit. It basically serves as a window into the prosthesis, visualizing the hidden movement patterns in the residual limb. MyoPlus ensures smooth and intuitive prosthesis control, smooth transitions, precise control, and more grip options. MyoPlus offers superior use of the hand prosthesis and gives the user freedom to concentrate on the essentials of daily life. MyoPlus, the new standard of care using artificial intelligence technology.
Okay, so this one of the one of the official video from Autobook. Okay, probably you can also search through online. And then this is for the lower limbs. Also, Acer is one of the famous company in the world, provide this kind of the video. Okay, you can see it. You can see together. Okay, in here, actually, this one is operated by implanted myoelectric sensor, actually implanted in the limbs, the lower limbs. So for the lower limbs, actually, this kind of the ambulation, the walking pattern is quite regular. So that there are only bionic limbs, okay, as own automative operation function. So without including any kinds of the intention of the user, but still work well. But point is, the issue is, whenever they would like to change their terrain, like just walking the plat, right? And then just happen this kind of the like some object, right? Or just suddenly something, appear in front of you, in front of the user. That kind of the situation, they cannot respond properly. Okay, so that's why still especially for the lower limbs, they need to include the user's intention for their operation. Okay, so this video shows this kind of the element, okay, this kind of the advantage of the lower limbs. Okay, then let's slightly change the gear. Okay, so we have talked about the passive, okay, prosthetics, and then to myoelectric prosthetics. Okay, so even though in those company provide the kinds of the kinds of solution and product, right? But still, in terms of the usefulness, I mean utilizing, it's in terms of the function of the bionic limbs has still limited. The why? Because as we already briefly talked in the previous previous slides, whether it depends on EMG electrodes. So as I briefly mentioned that even when they use quite longer and daily activity, when they become sweet, then it actually disrupt the recording of the muscle actually very seriously. So then for the ambulation, like walking function, if the bionic leg shows the malfunction, then it finally resulted in very serious accidents, right? That's why in terms of the safety and durability, actually so many things we have to solve it. Okay, so first one is the electrodes, surface EMG electrodes. So even though we place well and then provide a better surface EMG that we developed it before, right? The pressable and usable. But still the limitation of the recording because the muscle is under the skin. Okay. But electrode just putting on the skin and then it's slightly moving, okay, during some kinds of activity, that all these kinds of the pattern recognition algorithm and calibration have to do it again. They're also one of the serious hurdle to commercialize this kinds of application. So that's why still researcher would like to get signal from inside the sources like nerve or muscle. Also, our group also developed the microneedle EMG electrodes, which is really it shows a really good result compared with the surface EMG. So probably next lecture, if we have time, then I will briefly introduce that one. There is one advantage. One approach. We'd like to get more high level of the EMG recording, okay, reliably, okay, and very durably. And another approach is we can approach to the inside it. We put the electrode inside our body, okay? Because for the amputation, anyway, we already cut the nerve and the bone and muscle, right? So during that surgery, we can put our electrodes, okay? So let's see this one together. So let's say here is amputation. So let's talk about the problem of the amputation, okay? So amputation, one of the serious issue is actually phantom pain. Phantom pain means they already lose their limbs, right? But still they feel very serious painful phenomena, painful feeling like sometimes burning, stabbing, shooting, clamping from the one they already lost it. Okay, that's actually because of these kinds of neuroma. Okay, neuroma actually occur at the end of the nerve because the nerve should be stabilized somewhere like muscle and then have to do their own role. They have to function, show some function. But once they lost their final destination, then it become these kinds of neuroma, okay, generating pain, serious pain. So that's why in surgeon try to solve these kinds of the neuroma. Okay, sometimes they just remove the neuroma and then reconnect the nerve. Okay, and one really creative surgeon cut the nerve just near the muscle. The interesting part was the muscle, the nerve well settled down in new position in that muscle in here. Okay, and then another interesting part is once they stabilize well in this new territory, right, new muscle, then that area can be controlled by this nerve. Okay, they actually literally invasive in this area. So previous nerve, let's say I got kinds of the amputation in my finger, okay? So that nerve connecting to the finger, so now I don't have finger, right? But during the surgery, if a surgeon put my nerve to near its thumb, then I try to move my finger, okay, even though I don't have, but whenever I send the signals from the nerve, then actually some part of the muscle on thumb to move it. That is a really interesting phenomenon. Okay, so nowadays, that's why these kinds of the interface we call mechanoneural interface. So simply biological interface, we use it. Okay, so let me briefly explain this some more. And before that, when you look at the left side, so this is published, it's in New England Journal of Medicine. It's one of the really famous, okay, like some doctors said it's one of the Bible, okay, in the journal, really famous one. It published in 2020. So there is the transhumeral amputation, right? In here, and they lot of electrodes put inside it, like peripheral nerve interface and muscle interface, all the things. And then this kind of the connector is directly fixed through the bone. So this technology we call osseointegrated technology. So function is they directly connect bionic limbs to here, and then this also interface can transfer all the wires from the electrode to the outside it. Okay, quite interested and also quite creative method. So it worked well, especially for the lower limbs, but I heard that for upper part sometimes the bones break it. because of the heavy, okay, because of material of this osseointegration. But anyway, they produce these kinds of things. But nowadays, as I briefly mentioned, mechano-neural interface, okay, a lot of studies, okay, result actually reported. So let's briefly talk about this one. Okay, first one is a TMR. Okay, it's targeted muscle reinnervation. So idea is, so I briefly talk about one of the way of prevent the neuroma, right? The cut the nerve when they put near the muscle, then this nerve actually have kinds of the controllability of the some part of this muscle. So using this way, they put the several cut nerve to near the muscle, especially in chest, and then still they use the same neural signal to control the bionic hands, okay, by record the signal from the chest muscle. Okay, it's really weird, right? So here goal is to create more natural control of the prosthetic limbs while still using EMG as an input by rewiring motor neuron to intact the muscle. Okay, but when we look at this one, still whenever he tried to move the hand, then chest muscle continuously contracted, right? So actually chest muscle has own function and own role, right? But these kinds of the invasion, okay, actually cause a lot of fatigue and load to the chest muscle. So that this is what shows one of the possibility to use this kinds of TMR technology to use it. So TMR technology means cut the nerve, just putting near the muscle so that block the neuroma and then has the controllability of the muscle. Then by record the muscle signal, they can still have some actually acquire the intention signal, motor signal. That is a major idea. So recently, Science Robotics in 2019, so they tried to combine with the TMR with wireless intramuscular sensor. So just to put the implantable muscle electrode inside the muscle and then apply to TMR surgery. So just cut the nerve, just put near the remaining muscle, and then like coiling using whole the arm, and then wirelessly transport to signal to the limbs. That is one of the concept. So they did it in above elbow amputee, transhumeral, okay, and then long term, 2.5 years implant, wireless implant myonic sensor. Limitation is robot needs to change the shape of the soft tissue. 3 degrees of freedom of the prosthetic device, even though they put the 6 EMG electrode inside it, but only 3 degrees of freedom. Okay, so for example, 1 degree of freedom and 1. So probably another things, we can say another function like this one. Okay, 3 is actually really small. Okay, so especially for the hands, if we just include here wrist, the hand shows our human hand has the 20 degree of freedom. So one of the largest, actually really large number of the degree of freedom our hand has. Okay, so that 3 degree of freedom is really, really small, even though they implanted the 6 electrode in there. So low transmission and no sensor feedback. Okay, so probably we will talk about the sensor feedback later. Okay, so it means they cannot feel at all whenever they move it. Okay, so another interesting approach was, okay, so TMR work well. Okay, we can block the neuroma, and then even we can use the EMG signal. So one of the also creative surgeon, actually plastic surgeon in Michigan University, suggest, okay, then why don't we got kind of the muscle graft, okay? So definitely they use the patient graft, own graft, like slide, and then put at the end of the nerve, making kind of the wrap. You can think about the kind of wrap at the end of one, okay? Then still we can expect the same. It can reduce the neuromar, and then still we can use the neural signal, okay, as biologically amplify the muscle signal. Okay, so one of the critical challenges to record the neural signal from the nerve is amplitude is really small, so that removing the noise is really, really critical. Okay, but in this technique, these kinds of the nerve signal biologically amplify as muscle-like signal, so that amplitude is naturally biologically amplified. Okay, it sounds wonderful, right? So the large stable recording with intramuscular electrodes, functionally selective, because whenever they can separate the nerve fascicle by forming this kind of muscle, they record the muscle signal. Also can prevent neuromar and peripheral phantom pain, no moving of nerves, or the innervation of the existing muscle. So using this technique in Michigan University, actually published in this one in 22, Science Translational Medicine Journal. Okay, so they already implanted this kinds of the RPNI to the human, so upper limbs. Okay, and the multiple RPNI they form and inserted wire, the intramuscular wire. Okay, for muscle recording, and then using that signal, they achieve intuitive control, okay, direct control, quite a long time. Also, this woman still they use this one, okay. Still here when they wrist, she still manually rotated, right? So here key point is intuitive. Okay, for example, in previously when you talk about the pattern recognition, right? That one actually cannot be the intuitive control, right? So whenever we muscle some movement, right? Then once they define the muscle pattern and only using that pattern connecting to the specific just motion, okay? So, but this one case directly form the interface at the end of the nerve so that whenever actually she used their own feeling or controllability with bionic limb, like previous he did it in daily life. So intuitively, he can control the bionic limb without any kinds of the training or calibration of the bionic limb. So that is one biggest advantage in here. So it's published in here. And then another technology we call agonist-antagonist myo-neural interface. Actually, this is suggested from the MIT, the Professor Hugo Herr, who is a really famous guy. So you can see easily her in like YouTube, right? Any kinds of the video, okay? Because he got the lower extremity amputation, okay? So he'd like to develop the bionic limb for him, okay? That's why he studied and researched and become MIT professor. And he continuously present a lot of excellent, great work. So especially for recently, he published in Nature Medicine in last year, and this year also published in Science. I remember the Science. So lower extremity limbs combined with osseointegrate interface that I described before, right? So in this group, use this kind of the army technique, which is actually connecting to agonist and antagonist muscle together. Okay. So for example, you can think about here, okay, and then here. So once you got the empathy, then you just connecting your 이두 and 삼두 together. So which advantage we can take using this technology? So whenever he tried to move, let's say here front muscle, then the opposite agonist muscle naturally release, which generate the sensation, okay, sensory feedback to the user, so that they can feel it. Whenever they move their muscle in one or either way, they feel it, they can feel it. So naturally sensory feedback they can achieve only using this kind of the surgery. So also this is really exciting and creative approach. Okay. So this is army technique. So like this one. So like here, TMR technology or RPNI technology or like AMI. So these kinds of the neural muscular interface actually are suggested in recent days. And for the RPNI, also from MIT, another professor, and also the Paul Sedana, the plastic surgeon that I described before, suggests a lot of weird approach. So for example, in here, because we just connected, previously he just connected the muscle graft at the end of the nerve, right? But nowadays, to realize the real sensation, like pressure, temperature, okay, touch, only we can get through the mechanoreceptor at the end of our dermal. So they try to get dermal, okay, they detach the dermal and then combine with RPNI. Sometimes partially put half of skin, half of muscle from one nerve. Sometimes put the skin inside the muscle. So whenever they contract their muscle, then this mechanical movement actually provide the mechanical input to the mechanoreceptor, which naturally deliver the sensory feedback, sensory feeling. Okay, really weird, right? And sometimes they just put the skin at the end of the nerve. Then nerve also stabilize well on the skin. Okay, but this case we have to apply to like a physical input, right? Sometimes vibration, right? But temperature, whatever, even though this is located inside the body, right? So anyway, also these kinds of approaches really looks weird, but they tried it because these kinds of biological interface guarantees the long-term implantation because they have to use their own tissue so that no issue about immune response, which is a really serious issue for the neural interface, okay, like engineering-based neural interface. Okay, so probably also I will talk this one a little bit more in other classes, okay? So based on this actually background, also our group tried to combine both. So RPNI actually collaborate with the Asa Medical Center. Actually, that Asa Medical Center also closely collaborate with the Michigan University together so that they learn the skill of the RPNI and then collaborate with together. So we suggest the peripheral neural interface can be combined with RPNI technique. Sorry. So main idea is once we cut the nerve and then implanted our interface, okay, and then form the RPNI on there. So electrodes can be connected to the nerve. At the same time, electrode can be contacted to the muscle, RPNI contact within just one interface. So this is a basic concept. We did it 3 years before. So muscle electrodes, nerve electrodes, we can achieve both with one interface so that we can record the muscle signal as well as neural signal. Also, we can stimulate muscle and then also nerve. Okay, so for this one, probably also I will talk a little bit more in other classes, okay, other time, okay, when we talk about the application in peripheral nerve or bionic limbs. Okay, so this is a current trend. So even though there is still, how can I say, capability, okay, to control the bionic limb using EMG-based myoelectric system, but as I briefly shows in this class, still limited. A lot of limitations still exist. So that's why we cannot see like bionic limbs in around us, right? So based on the statistical result, right? There are a lot of patients in the world, in our even our South Korea, in our country. But why they don't use it? So because of the function, okay, which is not actually cannot satisfy the patient now. And another thing is still quite expensive, really expensive, all the things. Okay, so probably that's why nowadays, this kinds of the peripheral nerve interface based bionic limbs, and of course, via the central nervous system like brain or spinal cord is possible, or in suggestion from the medicine field, like mechanoneural interface, okay, using the biological interface, also suggested recent a few years. This is one of the trend, okay? So what's next? So we can think about it. And I'd like to show this video at the end of today's lecture. So this video is the really old video, but when you look at this one, whenever touch, like actually poke, right? To pinch at the end of the finger, then he directly responds. Okay, you see that? This is a simple phenomenon, right? Simple response, but in human, right? But in neuroprosthetic system, that is really complicated, okay, process. So chip. So first, whenever they picking the finger, right? Then sensory signal directly deliver to the nerve, okay? Then that signal passing through the spinal cord and the interneuron, okay, and directly reflect to muscle signal, okay, and then that signal directly respond to the finger, okay. There is natural response in human, but in prosthetics, we cannot achieve now. But this one, as like movie, we hope we can see like this phenomenon soon. And then, yeah, like also this one, finger movement, literally. Yeah, so in terms of the graphic, the detail is not clear, right? But anyway, it seems like connecting to the bionic limb to nervous system level, fiber level, okay? So I hope we can achieve this kind of the function in near future. Okay, and then I will briefly talk about the homework. Okay, as I mentioned, so lecture video cover 1.5 hour, okay, one class, and the other class I'd like to you guys spend time for preparation of the report. So I call this homework day. So I just list up like some YouTube regarding for prosthetics limbs. Please look into it, and then if you want, you can see more. You can look the more video. Actually, there are a lot of videos. So if you are interested, you can get a lot of information. Okay. So once you see all these kinds of the video, and then you can prepare the report. Okay. Let's here briefly talk about report assignment. So bionic limb interface design. So imagine you must design a new bionic limb interface within the next 10 years. So bionic limb interface. So like clearly describe which kinds of the sensor or electrodes or feedback system you'd like to combine. So you can suggest, okay? It's with your imagination, okay? But that sounds plausible, right? Okay. And then I would like to let you sketch, okay? You can just feel free to sketch location, okay, electrodes, which type electrode there. So today, even though we just cover like passive or bioelectric based and partially neuromuscular interface, but next week and after next week, we will cover more content regarding for binding limbs, right? So that you can study well till at the end of my last lecture. So I just set up deadline is you have enough time. Okay, so you don't need to write down now, but you just try to think. Okay, and then listen the class, then you got more information, more kinds of insight. Okay, so I'd like to you guys include at least one sketch, okay, and comparison diagram, whatever is okay. Yep, hand drawn, okay, and evaluation. So you'd like to determine the advantage and limitation yourself, because it means once you describe well, you know well about all the components, right? And then creativity, okay, not just the summarizing existing materials. So there are nowadays a lot of the AI tool in there, right? So you can use it, right? But not just to summarize and put the report. Just I'd like to show you on your creative idea. So very fresh and interesting idea. I'm really welcome. And personal experience and thought, okay, you can use it. So connect your design with your personal experiences or insight. Okay, just an example. Okay, format. Report must be handwritten in Korean. So you can just write in Korean clearly, but handwrite. Okay, handwrite. Okay, even just digital pen will be fine. But anyway, you need to handwrite your own word. And then maximum page 10 page, excluding references. You should put the references, but you can put after 10 page. Still, you can use the 10 page from your starting point. Okay, references, really important, right? You should include it. You must include the reference. You must include the references. Submission, you can send to the TA, Young Kim, okay, by October, the 1st October. So actually, right before start the new class from probably Professor Okyun Lee, yeah, another professor, start team teaching, right? So before that, you can just submit it. Probably after finish my class, you still have 5 or 6 days, okay? So please make sure the file name clearly. You have to put report like bionic limb, student number and name. Also, student number name, you have to put inside the report. Okay, this is really basic things, right? Like here. Okay. Okay. Use of AI tool. The use of AI tool is allowed. Okay. But you must explicitly state where and how you use them. Okay. Example, I used the ChatGPT to check the grammar in section 1 and some kinds of simple summary. It's okay, but you just think, okay, write your own word once you saw the summary, right? Then we'll be fine, but you have to specify in here. So it's gonna failure to disclose the AI use will result in the grade penalty. Okay. Okay. So this is the all of my lecture today that I prepared. And then regarding to the report assignment, if you have some question, also you can give during the lecture or via email, so we will find. Okay. 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 Thank you for your time.